E-waste is one of the most prominent waste issues that the world faces today. It is one of the rapidly growing solid waste streams worldwide, expanding at 3 times the rate of the global population. Despite this, only a small fraction of e-waste was recycled in 2019. According to the World Health Organization, in 2023, approximately 53.6 million tons of e-waste were generated worldwide in 2019. Yet only 17.4% of this amount was officially collected and recycled. According to Rautela et al. 2021, e-waste management is often ignored due to the requirement of the high capital investment to recycle and treat such materials. Although some countries allocated budget to control e-waste, in many developing countries, e-waste is treated and handled informally in uncertified manners.
In recent years, there has been increasing concerns about the environmental implications of lithium batteries. Studies have demonstrated the negative environmental effects of lithium batteries, which can contaminate, damage, and destroy soil and water resources. Additionally, spent lithium-ion batteries, or LBIs, are classified as hazardous waste that pollute the environment and harm both animals and humans, according to Zhang X et al. 2018. Due to the emerging problem caused by waste from expired batteries, recycling batteries has been receiving attention, and some countries have implemented recycling programs. However, battery recycling still needs significant improvement as the process is not environmentally friendly and emits carbon footprints that harm the environment while also being costly, according to Jerva 2021.
Another solution to the problem of battery waste is biobatteries. Recently, it has been made from aloe vera called aloe isel, developed by Sharma and Suman in India, and has been commercialized according to Traxin 2024. There has also been a few attempts to develop new biobatteries from different plants of fruits with potential energy. An example of this is the fruit waste as an alternative electricity source researched by Saitoros 2024.
However, all this research and development efforts has been conducted in different countries. The aim of this research is to develop a biobattery that could be easily made in our country, that is from something that is accessible really around in our country, such as papayas, which grow abundantly in tropical regions according to Dallas News 2013. Moreover, papaya seeds are relevant byproduct generated within the fruit processing industry and frequently disposed as the waste. Previously, studies demonstrated the potential of papaya to generate electricity suitable to various applications according to Chua et al. 2013.
The objective of this study is to develop and evaluate papaya utilization as alkaline biobatteries using its seeds.
1. What is the minimum, average, and maximum voltage of the following? A. Poles. B. Commercially available batteries.
Is there a significant difference between commercialized battery and pulse in terms of A. Minimum voltage, B. Maximum voltage, and C. Average voltage?
This research will investigate the use of papaya seed as an electrolyte to improve biobattery performance. The study will assess the viability of papaya seeds as sustainable battery. By reviewing recent research, it will explore factors influencing biobattery performance and evaluate the suitability of papaya seeds. The focus will be on the overall performance of biobatteries using papaya seeds and their relationship with other performance factors.
The study will not examine advanced aspects of biobattery performance such as detailed electrochemical processes or specialized engineering techniques. It will also avoid an in-depth analysis of complex chemical components of papaya seeds or the biochemical reactions. Instead, the research will provide a broad overview of the practicality of using papaya seeds in biobatteries, emphasizing their basic characteristics and general performance trends. This study shows significance in different categories, namely sustainable energy source, local economic development, reduction of environmental pollution, contribution to climate change mitigation, and educational and scientific advancement.
It is a sustainable energy source as it presents a sustainable alternative to a conventional battery and by repurposing agricultural waste that contributes to reducing papaya waste and promoting eco-friendly energy solutions.
While it also has the potential to create new opportunities, particularly in regions where papaya cultivation is widespread, Hence, this innovation could stimulate local industry centered around waste management and renewable energy production.
It can also reduce environmental pollution by reusing this waste into biobatteries. The study offers a solution to mitigate environmental pollution associated with agricultural waste.
It also contributes to global efforts to solve chemical change. The reduction of greenhouse gas emissions associated with conventional battery production and disposal aligns with sustainable development goals.
And lastly, it contributes to the body of knowledge in biobattery and organic waste utilization, offering valuable insights for future studies and scientific advancement. Moreover, it provides educational opportunities for students and researchers interested in sustainable energy and waste management.
According to recent studies, papaya, a tropical fruit renowned for its sweet taste and nutritional value, offers promising components for batteries application, and one in particular is an alternative energy production. The components of papaya relevant to energy generation including its fruit pulp, which contains sugar organic compounds suitable for microbial fuel cells according to Akpotayire 2020.
Additionally, papaya waste including peels and seed holds a potential biobattery materials according to SCOOM 2024. Papaya's organic matter, especially its sugars and carbohydrates, can be fermented by microorganisms in microbial fuel cells to generate electricity. Furthermore, papaya waste can serve as alternative source of energy through chemical processes that release electrodes for biobattery applications.
In addition, in the Philippines, papaya is abundant year-round, making it readily available resources for sustainable energy solutions, according to TASHO 2018. This year-round, availability facilitates its utilization in various fields, including medicine and scientific experimentation, highlighting its multifaceted significance.
According to BioTech Articles 2023, biobatteries are emerging as a superior alternative to conventional batteries due to their renewable and sustainable nature. Unlike chemical batteries, they do not pose risk of explosion or leakage, making them extremely safe to use. Additionally, according to Singling Insight Taurus 2024, fruit waste including peels and other organic matter can serve as an effective biobattery materials. The production of biobatteries is eco-friendly because it involves biodegradable components that significantly reduce environmental pollution compared to traditional batteries, which often contains toxic chemicals and heavy metals.
Furthermore, research from Nazimuddin et al. 2022 also points out the cost-effective of biobatteries, especially in the regions with abundant agricultural waste. This makes biobatteries a practical solution for sustainable energy on finite and environmentally damaging resources used in conventional biobatteries. In conclusion, biobatteries represent an innovative approach to sustainable energy, offering safety, environmental benefits, and costly effectiveness.
According to Takamura 2009, alkaline manganese zinc batteries are highly favored for powering portable devices due to their reliability and convenience. They excel in heavy-duty discharge scenarios, providing extended power even under continuous heavy load and low temperatures. Moreover, they have a longer storage life, are leak-proof, and reasonably priced. As noted by Safru et al., alkaline batteries use zinc and manganese dioxide electrodes with an alkaline electrolyte, offering a steady voltage and improved energy density compared to carbon-zinc batteries.
Despite a market shift towards rechargeable chemistries like nickel, metal hydride, and lithium ion, alkaline batteries remain dominant due to their availability, reliability, and versatility. SCOOM 2024 highlighted that alkaline batteries introduced commercially in 1950s have become common household items, boasting a high power density and environmentally friendly mercury-free construction. According to BJUICE, their high energy density, consistent performance, and low internal resistance make them a popular choice, outperforming zinc-carbon batteries in different density and shelf life while maintaining the same voltage output.
The first phase is the gathering and authentication of the materials, in which the papayas will be from a local supermarket in Pinakayan, Kawit, Cavite, and will be authenticated at the Bureau of Plant Industry, BPI, located in Metro Manila. Essential components such as the battery case, Wax paper and sealant will be procured through online shops. The researcher will also obtain a steel tube, brass nail, and an LED light from a local hardware store, while the voltmeter, pounding tool, and a fruit processor will be provided by the researchers themselves.
Second phase is preparation of papaya seeds, wherein it was divided into three parts, such as powdering, preparing paste, and the potassium hydroxide extraction. For the first part, which is powdering, seeds will be collected from 2 ripe papayas and dried in the sun for 120 hours. The dried seeds will be then pressed into a food processor to produce powdered papaya seeds. The second part is preparing paste, in which seeds from 2 ripe papayas will be collected and powdered into mush, creating a gel-like paste suitable for the use of battery. And for the last part, potassium hydroxide extraction. The seeds will be combusted to produce ashes, from which potassium carbonate is produced. This carbonate is then reacted with potassium hydroxide to produce potassium hydroxide. On the other hand, the sodium hydroxide method involves alkali soaking, acidification, bleaching, and water extraction, while the calcium hydroxide extraction process involves acidification, alkali extraction, and carbon dioxide neutralization, with concurrent dosification and agar extraction during alkali extraction.
For the third phase is the construction of the battery, in which firstly, the case made up of steel tubes would be cut and prepared in 2 inches in length and around 0.5 inches in diameter. After this, the powdered papaya seeds are put on the sides of the battery case, imitating a ring. This would represent a cathode. A sealant would then be put at the bottom of the case. Then a piece of wax paper would be around the inside of the cathode ring, and the extracted potassium hydroxide will be injected as the electrolyte, and it will be absorbed uniformly by the cathode ring in the paper. After the absorption of the electrolyte, the anode material, which is the paste and the mashed papaya seeds, is placed on the inner part of the separator. Then a small brass nail is placed in the middle of the paste as a current collector. Then finally, seal the battery with its upper edge bent over the stopper. Then the battery would undergo static aging for about 2 weeks.
For the next phase, which is the testing, 5 batteries will be made and it will be tested in voltmeter for 3 times to get the minimum, average, and the maximum volt of the battery. A commercially available AA battery would also be tested using a voltmeter in the same amount of trials. The biobatteries would also be tested on LED lights to see if it could actually be in use.
And for the last phase, data analysis. The volts resulting from the voltmeter of the biobattery and the commercially available AA battery would be compared using an independent sample t-test. The independent sample t-test would be used twice to compare the results of the minimum, average, and the maximum volts, with the meat biobattery as the treatment group and the commercially available AA battery as the positive group.